All right, this is Deep Thoughts with Deegan, and today what I'm going to do is I'm going to talk about some derivative shortcuts. And the reason I'm going to do this is because honestly, I think it's pretty cool how you can find these shortcuts a lot of times. But also it's pretty useful because one of the hardest things about calculus is that there's so much to remember. So having these little shortcuts prevents you from having to do 50 extra steps sometimes. If you have a really big differentiation problem, sometimes you can just use these to skip a chain rule or a product rule. And a lot of these work because the natural log and e to the x have very simple derivatives. So this is the first one I'm going to talk about right here, the natural log of some function f of x. This works with any differentiable function. Now, if I'm just looking at the chain rule, right? I'll just set up the chain rule right here. I got my little table, which is always helpful, right? So we got ln of x, derivative of that is 1 over x. F of x is our inside function, derivative of that is just f prime of x. Because these two functions, well, f of x just has to be differentiable, and f prime of x just has to exist. And if we plug things in, we get, well, we plug in the f of x to the x, so we get 1 over f of x. We're going to multiply that by f of x. So what that's going to end up being is f prime of x divided by f of x, which works out for some pretty cool things. So like, for example, I'll do cosine of x. The derivative of the ln of cosine of x is actually just equal to, first of all, the derivative is negative sine of x over the function itself is cosine of x, is just equal to negative cotangent of x, which is actually kind of cool how it works like that. Same, very similar. The derivative of sine of x, ln of sine of x, is equal to positive. Yeah. We have cosine. This is tangent. This is tangent. Sine over cosine is tangent. I got that mixed up with this, where we get cosine over sine is cotangent of x. See, even I mess these up all the time. So this one is one of my favorites. All three of these are so useful. A lot of these random shortcuts you don't get to use very often, but these three that I'm showing today, I actually use them quite a bit. The next one I want to do is the derivative of some function in terms of x times e to the x. This is just a product rule. So we're going to have e to the x. I'll do it right here. E to the x. Actually, yeah, I like having e to the x first. So we're going to put e to the x first, right? We're going to have e to the x times f of x, because I usually start with the derivative of whichever one I want first for the product rule. And then here, we're going to have e to the x f prime of x, because now we have this times that's derivative. And if you look at this, we can factor out the e to the x. So we end up with e to the x f of x plus f prime of x. And this does some pretty cool things. Like, something I've been working on is finding the nth derivative of x squared e to the x, or just x to the n e to the x. And looking at this, what happens is if I have, let's look for the second derivative of x squared e to the x, right? Well, according to this, what that's going to become is the derivative with respect to x of e to the x squared plus 2x. And in this case, I am actually going to expand this to e to the x, well, x squared e to the x plus 2x e to the x. Because now if I'm going to take the derivative of this, it's going to go further. We're going to have e to the x squared plus 2x plus 2, because that's a constant coefficient. That's a that looked like a gamma, 2 e to the x plus 1. And it'll keep like getting bigger and bigger, which is why it's hard to have an exact formula for it. But that's what happens here. So actually, this one's pretty cool, because it shows up a lot. All three of these actually do. So that's why I actually use these. They show up so often, and in calculus, you have to do so many different steps that these simple shortcuts can make everything so much easier. So for the last example, I have the derivative of e to the f of x, and there's a couple cool things you can find here. First of all, let's just look at this chain rule wise. The derivative of e to the x is e to the x, so I'm going to plug in the f of x. So we're going to have e to the f of x as one of the factors, but we still have to multiply it by f prime of x. So this is going to be equal to f prime of x e to the f of x. And I want to show you two examples. First one is kind of easy. You can prove the nth derivative of e to the ax using this. So like if I have e to the ax, the derivative of e to the, that's really small. If we have the derivative of e to the ax, where a is just a constant, that's going to be a e to the ax. And if you notice, that's a constant coefficient, so it's just going to multiply by a every time. That's how we get the formula, the nth derivative of e to the ax with respect to x is just equal to a to the n e to the ax, which is pretty cool. But another one that I really like, just because there's a lot of stuff happening, but it's not terrible, is the derivative of e to the x to the x. So first, the derivative of x to the x is pretty well known, but I'll just work it out quickly. So x to the x, you can't just differentiate this directly. You have to use logarithmic differentiation. So we're going to use the derivative with respect to x of e to the ln of x to the x, which you can take the exponent out, so you end up with x ln of x, right? The derivative of x ln x is going to be, I'll write this down here. The derivative of x ln x is equal to, this is a product rule, so we're going to take the derivative of this one first, that's 1. Derivative of natural log of x is 1 over x. I don't take the derivative of both of those, that's wrong. Actually, what you do is take the derivative of this one, you don't take the derivative of this, so that's ln of x. Now we keep this, multiply it by the derivative of ln of x, which is 1 over x. So we end up with x over x, which is going to be 1. But also there's a little bit of a domain restriction there where x can't equal 0, which makes sense. We already have a natural log there. So we have that there. Now we can just chain rule this. And we can use the same rule right here, where we got, now this is going to equal ln of x plus 1 times e to the x ln of x. Okay, so now I have this, and using this formula right here, I can plug that in. So we have, first term is ln of x plus 1. Second term is e to the x ln x. Third term is ex to the x. And also, if you're doing another step of differentiation, instead of having to do a product rule here, you can just combine these exponents where we get ln of x plus 1 and e to the x ln of x plus x to the x. Those are just a couple of the ones I use, but these are like the biggest ones, especially with anything involving e to the x, because the derivative and integral of e to the x is e to the x, which kind of makes it act as a kind of stabilizing thing, which I think is pretty cool. But anyways, that's the end of this video. Hopefully this was helpful, and I'll see you next time.